Good afternoon, everyone. I'm Shuhao from Meta, and I'm a hardware analytics engineer in infrastructure release to production team. And this is my teammate Richa. Today, we are going to introduce the hardware utilization effectiveness and the related studies we are working on. So over the years, we have seen the rapid growth for the power usage in infrastructure data centers. It's very important for us to have a metrics which can describe how effectively we are using the power in the data centers. So where we can know where we are and where's the opportunity to improve the power efficiency. Green Grid has introduced a metric called the power usage effectiveness, which is PUE at 2007. So it is defined as the total data center power divided by the total IT power. Several years ago, when Meta first calculated PUE, we are at around 2.0. And in the most recent sustainability report, we have already achieved PUE at 1.09. So you can see it's a really huge success. But you can also see that we are almost squeezing out the opportunity at the PUE level. So within the IT power, we also want to have a metric which can describe that how effectively our IT gears use their power. That's why we define the HUE, the hardware utilization effectiveness. So HUE is defined as the total IT power divided by the information processing power. It can be calculated at different scales from a single component level like a CPU to the system, the rack, even the data hall level. So it's very useful to characterizing the power efficiency for our IT equipment. So how do we calculate the HUE? As I mentioned, HUE is defined as the total IT power divided by the information processing power. So the information processing power can be further expanded as the IT power minus parasitic power. So the parasitic power here, we just want to describe some power that is not directly related to the functionality of this specific server type. It includes the hardware tax, like it should be the idle power when the hardware just sitting at the data center with the minimum operating system and running some necessary software required by Meta. And also, it should include the thermal keys, which is the power consumed by the cooling equipment like the fans and pumps. Also, we'll have the thermal leakage power. We model this, use some mathematical way. And what's the opportunity of the HUE? So basically, we can reduce HUE by anyways. In this way, we can improve the hardware efficiency. So before this, I want to introduce another concept. It's called the minimum attainable HUE. So this is basically given a piece of hardware, what is the minimum possible HUE value that this hardware can achieve. So it usually happens when the hardware is running at the highest efficiency operations. So if we want to reduce the HUE overall, basically we have two ways. One is trying to reduce the minimum attainable HUE by some design improvement. So it will require us to leverage some hardware techniques to reduce the idle power for the hardware components. It can provide some guidance for us for next generation hardware design. But if the hardware is already sitting at the data center, it's kind of difficult for us to reduce the design idle power anymore. So we'll have the second way is trying to approach the minimum attainable HUE by some operational improvements. So like we can narrow the gap between the operational idle power in the data centers and the design idle power when it's tested in the lab. So basically we can optimize the necessary service required by the data center. We can also try to encourage the lower power states when the server is at idle. And also, we can be more effectively arranging the service to the host. So we'll have the service placement started later. So this year, other than this basic concept, we also want to introduce 3 studies we are working on. So the first one is I want to talk about the process that how we define, build, and monitor the HUE for a new hardware type. So the first step is to define the HUE equation for this new hardware. In this step, we just want to answer a question. Okay, so what is the information processing power for this specific hardware? Like for general compute server, it should include the non-idle part of the CPU power. Like for a storage, is a storage server, we should need to consider the power for the disk I/O. And also, we need to figure out the hardware tax, the thermal keys, the leakage power, and at the end of the day, we should have a HUE equation for each hardware type. And the second step, we are going to build a data pipelines to continually support this HUE calculation. We need to write some script to collect the values from the power sensors in our hardwares and save it into a database for a longer retention. And then we'll build a pipeline to calculate the HUE on a daily basis and do some aggregation at different granularity for further investigation. And the third step is we are going to build a dashboard to visualize this HUE across different hardware type like compute and storage, also across different service. So that will provide us more insight that where is the opportunity to do further hardware efficiency improvement. Now the HUE framework has already covered more than 93% servers in our data centers, so which is already a majority in our fleet. Okay, then I will pass to Richa to introduce the rest of the two studies.
Thank you, Shuhao. Continuing with the other studies that we have done with HUE, a main goal of these studies has been the opportunity for HUE and how do we realize those opportunities that we see within our data centers. This study particularly focuses on the service placement utilization and the correlation of hardware utilization based on service placement. We also compare the current chassis agnostic service placement process within a shared chassis and doing a chassis aware service placement and how that affects overall hardware utilization. Coming over to the shared chassis configuration, this is a view of different ratios of idle versus non-idle hosts we can have in one particular compute chassis. Within this compute node, we have 4 different hosts, and at different points, we go through each of these options of having 1 non-idle host and all the way up to having 4 non-idle hosts. So the background of the study is covered across this compute chassis, which houses multiple servers with the shared chassis configuration. The services are currently placed in the chassis agnostic process, and that's how we monitor all of the power utilization and hardware utilization trends. This study was to analyze if the service placement is affecting the hardware utilization effectiveness metric that we have defined. We have both the high utilization based services as well as the utilization of less than 10%, and this was majorly done to have maximum coverage across all the different hardware as well as the services that are running across those. Coming over to the hardware utilization values across these utilization ranges, we took the data across 3 different data centers, and the buckets that we experimented on ranged from 10%, 40%, and 80%. Here, we have looked at the above 80% utilization bucket because that was representative enough of the trend that we were seeing across all of these data centers. We do see that there is a clear reduction of the HUE value from 1.46 to 1.32 when we go from 1 non-idle server to 4 non-idle servers. Now, what does this mean in terms of the overall hardware utilization? It does mean that when we have 4 non-idle servers on a single chassis, that makes the hardware more effective rather than just having 1 single non-idle server. And this can be used for several guidance and the feedback process during the hardware design and the early hack phases. Whenever we go through the IaaS steps, one of the steps is the service allocation. And this could be a feedback that goes in order to do the dynamic allocation of these services across these particular hardware chassis. Coming to the power distribution, we noticed the similar trend being maintained across the different platforms where we noticed this hardware utilization trend. So essentially, if we have 1 non-idle server, the overall power utilization will be lesser. And when we have 4 non-idle servers, the power utilization is a bit higher. This is expected because we have 4 different hosts, and each of these are working at almost maximum utilization. Now, it does mean that there is a single trade-off that we are trying to look at. The overall power utilization, when we look at this several clusters of the hardware, is still better than when we have several clusters of one single non-idle server working across these chassis. So the overall results here were the 14% improvement in the HUE value when we saw all of these servers in the chassis as non-idle versus one server as non-idle. And this applied generically to both low utilization and high utilization services. Going over to the next study that we did across different CPU generations, here we drilled down to a further CPU level and the HUE values over there. Shuhao previously covered how we calculate the overall HUE value on the hardware platform level. Here we looked at the CPU level HUE value and the computation of that and the correlation of services with that. So to define the CPU HUE value, we took the initial definition of the platform level HUE. So we have the CPU power, and we take the ratio of that with the delta of the CPU power and the CPU idle power. All of these samples have been taken at a 20 minutes interval across our sensors within these platforms. The reason we picked the 20 minutes interval is because of a parallel study called frequency polling study, where we noticed that whether we have a 4-minute sampling interval versus a 20-minute sampling interval, the total error rate was close to 1%. This made it more efficient in order to compute as well as store this data. So comparing the CPU idle power and HUE, we had two different idle powers that Shuhao touched upon before. One is the design idle power, which is the readings that we take from the lab. And the second is the operational idle power. These are the idle powers that we notice and use from the data centers in the HUE calculation. As of the summer, we compared 3 different generations of the same CPU, and we looked at the overall idle power across these and the operational tax value across these. We do notice the similar trend of the HUE value. So the higher up we go for an HUE value, it gets worse. But we also take into the account that every hardware platform, as we evolve, becomes more and more complex, thereby increasing the overall baseline of the HUE value that we are noticing. And that's the trend that we wanted to capture here. Coming over to the correlation of HUE with the utilization buckets, on the left side, we did see that the overall, the lower the HUE value, we do see that the higher is the CPU utilization, which means that the hardware is better utilized when we have the higher CPU utilization value. Within the low utilization range, there is more divergence in the HUE values itself, which means that the hardware is worse in overall utilization, and the services in this bucket would greatly impact the HUE value. In the high utilization range, we notice that they are more concentrated in the overall HUE value, and they tend to remain stable. And services don't impact much in the overall HUE. However, within the 10% range, be it for different generations of CPU or for different services that have been placed, we notice the similar trend. So call for actions and some of the next steps. We are currently working on expanding this framework to network devices, GPU servers, and investigating ways to reduce the operational idle power. We're also exploring the service stacking on hosts based on the CPU utilization studies. And we're planning to cover the HUE metrics in the Meta Sustainability Annual Report. We're also working on publishing the HUE white paper. Call for action here is if you or your team is looking at any particular hardware utilization metrics, or this is something that can add to some of the refinement metrics that you're looking at, please contact us or Jayati, who is joining us in the audience, and she's running a lot of this on the hardware engineering side at Facebook. Meta, let us know if you have any teams looking at this, and we'd be happy to collaborate more in our ongoing forum. Thank you so much.
Thank you.